this comes first and then this one, so don't copy it this way. Here here k 0 to 1 to 1 to m minus 1. Why? 0 doesn't come into picture at all. I am coming to that. In fact, it is written here. We will discuss that in just. Anyway, even if I made some mistake, you can correct it from the notes. I need that those intermediate results. That's why I have put it on the board. So if there is any mistake there, you correct it from that paper or from the book. Okay. So we were discussing this linear prediction analysis of speech. Maybe you should switch off that fan. It's not helping anyone. The reason is it's only making noise. Okay. So we were discussing this linear prediction analysis of speech, and as I told you, there are is the most powerful technique applied in many domains and in speech in particular. And in the last class, we mentioned what is called the basic formulation. And which is called the mean squared error formulation. Suppose we have seen that, and that resulted in what is called the normal equations, that is summation ak or n minus k is equal to minus of or m, k is equal to 1 to p and m is equal to 1 to p. So these are the normal equations, and by where Rk or Rm is simply Sn plus n plus m, summed over n. So given the data, that is the signal, let's say in this case speech, over n samples or some block of data, then you can see that you can just compute these what are called the autocorrelation coefficients for different lags that you need. In this case, you need up to p. In fact, you need up to p plus 1, and R0 is implied here if you write down that. Okay. So you can compute this from 1 minute. So this is called the basic formulation or the mean squared error formulation. And in the last class we discussed in detail the other types of formulations or interpretations, whichever way you want to look at it. And one is what's called, I am not going to repeat any of them except inverse filter formulation or interpretation, whichever way you want to look at it. And then the autocorrelation matching. Interpretation, and of course associated with this, although I didn't do this in the class, it is called the maximum entropy formulation. And we did what is called the spectral matching formulation or interpretation. and there are a few others. I list one or two, but there are how many? At least I know about 20, but I think there must be at least another 100 more different types of formulations. So it's basically what it means is how you look at it. That's how you interpret it. I'll just list down a couple of them, but without much explanation. One is what's called the maximum likelihood formulation, and the lattice formulation, etc. In the lattice formulation itself, there are at least about half a dozen varieties of formulations, which will just primarily meant for hardware implementation. So it's a so there are many, because there are many issues here. Obviously I cannot do all of this. Just the discussion of the formulations itself, formulation, I am not even talking about interpretation, is a full 1 semester course. That's the, because again, why can't you just leave it one of them? Different interpretations will give you different insight into the problem, because which problem you are addressing, after all that you have is sequence of n numbers. From which problem this originated is not known. If you know, then accordingly the interpretations will change. That is the reason. And also what you look for and what you don't want to look for. So that is what is important. In some cases, as I told you, if it is a medical signals problem, the doctor wants to look at the small kinks somewhere there, and which you cannot even understand. You keep wondering why should you worry about that small kink kind of thing. That's what, whereas in the case of normal representation by engineers like us, what we think is all right, most of it, gross in some number of bits you have to use, give enough number of bits so that the error is small kind of a thing. But it is still the error will never be zero in your representation, and you think that you have done a great job by making the error 10 to the power of -6 or something. But for the doctor, that remaining part is what is important, and whereas for you think that you have done a great job here. You see? So it all depends on various ways. In fact, it's a very interesting story. This whole thing, it's about it's a more than 100 years old story. It's not just 1 day, 2 days, and it keeps going strong. In fact, those of you who have heard that Shastra's lecture recently, the first video conference lecture from TI, how many of you have heard? Okay. In fact, the reason why people invited him was, although maybe most of the people who invited don't know, but was for the Texas Instruments contribution in fact, they put that idea of lattice, not really formulation, but synthesis in a chip in as early as 1977. So that is why, and for just $35, you could get a LPC synthesizer, and which could be sold for as a children gadget. That is what is called a speak and spell, where you just press a button. It's obviously you can't have the memory to store all of that, so you can just press a few keys and it pronounces a word. You see, so it used this kind of course it's a very interesting subject, not just interesting out of for intellectual curiosity, but interesting from practical angle. And the various, in fact, in spite of highlighting all of this, a lot of students and also even researchers make a lot of mistakes here, because they don't want to interpret this. They want blindly use a formula, but unfortunately it is not the case. In fact, what we will do whole of today, hopefully I will complete discussion on this today, otherwise tomorrow also, is only the interpretation of various, not this formulation part of it. And so it's okay. So this is about the linear prediction. You notice, although I am not repeating what I said last time, but each one gave some insight for us. In fact, as I said, you should never miss the words or meaning of words here. Linear prediction. So start with that. Prediction, there is some prediction. It is a linear prediction. So with that in mind, you started formulation, and then you ended up in a set of normal equations, of course, with a minimum error as summation ak rk 0 to p. And not only that, out of that when we started interpreting it carefully, what we have noticed here is that it results in a modeling a source production mechanism, in this case speech, as an all pole system, that we have already done, and where the model Hz is given by G by, you recall that Hz, the all pole model for this is simply given by G by Az. Notice that this is only or G by Az or 1 by Az is also fine, because G can be taken care of by error itself. So you can excite this system by which is 1 by Az by that error, G is automatically taken care of. On the other hand, if you normalize the error by its energy, then G should be put back here. So all these are certain things, but I don't want to go into detail. But the key idea here is that this formulation automatically leads, and hence you also say it's an all pole modeling of speech. All pole modeling of speech. And subsequent discussion, you notice that especially the spectral matching, I spent some time on that for the simple reason that gives insight for this. What is this all pole modeling do? What is this pole? What is meant by all pole modeling? That means, given a speech segment, you want to approximate its spectrum envelope by means of few peaks. That is a pole. Each one is a 2 pole complex conjugate pair. So you have number of peaks like that, and you by giving a fixed number, let's say if you make p is equal to some number, let's say 10, you can maximum 5 peaks is all that you can put, because each peak corresponds to a complex conjugate pair. You see, a pole pair is only this one. And notice that it has to be away from 0, because if it is 0, then all the resonance will be at the origin. It has no meaning. So if it has to outside the origin, all of you understand what I am saying. In the Z domain, you have to understand, if it is not at the origin, then it has to appear as a pair. So if that appears as a pair, if there is p roots, means maximum p by 2 such pairs will be there. So you decide a priori. If p is equal to 10 or any p you decide, you can only put p by 2 peaks, and where to locate these peaks and what width these peaks should have is dictated by the envelope of the spectrum. Get the point? And also what we have noticed here, and it's a very interesting and important, why linear prediction has become so popular in speech as opposed to many other domains, is because it tries to approximate the peaks better than valleys. There is a bias towards approximating the peaks than the valleys, and it is better by that way, for the simple reason that any day you can see the valley in a spectrum as a function of omega is more vulnerable to noise. If there is some background noise of a constant, this one, you can see that it is the valley that gets affected first than the peak. And so if you are able to perceive speech even in the presence of background noise or something, it is primarily because there are peaks here. You get the point I am saying? And not because, in fact, that is also the reason why you can see, of course, it takes a little more time to understand this probably, but you should all put all the knowledge of DSP that we have discussed in the class to appreciate this point. It is also the reason why you can see invariably over a telephone you have a problem in distinguishing M and N. That's why all the time you keep saying M as in Mary, B as in N as in Nancy, something like that you keep saying, because it is not that N you recognize it is the Nancy, the rest of it forces you for, hopefully there is no Mancy, so it's only Nancy. You see? So you can see why this M and N, although they are nasal resonances, the distinction is both are nasal resonance only. The distinction is because of the 0. The 0 in the case of contributed by this vocal tract, closed vocal tract, and you can see it is the 0 that you perceive. And the moment you talk about a telephone or a background, typically the energy is higher, so the resonance, the 0 or anti-resonance you call it, due to coupling, is the one that is first affected. That is why your perception is on. Because still sometimes you perceive primarily because, not because you perceive 0, the influence of 0 in the adjacent resonance. What should have been normally a resonance like this, what happens is it gets like this, screwed up like this. So you see this, you see this, instead of drooping like this, even though this got merged in noise, because of this shape of this got modified because of this, that is what you perceive, and still somehow your ear makes out that, oh, there is some resonance, or M and N you are able to distinguish. It's very, you can see how the influence of that on this. Okay, but otherwise you can see mostly this is vulnerable, and it's a challenge. In fact, even today, this, but then you may wonder why those sounds are produced in the first place. So again, you can't ask such questions, but the point here is, it is not meant for, you see, speech is not meant to transmit over your junk channels or lung. You are supposed to talk to each other, that's all. That is how the speech is meant for. Rest of it is all your innovation. You want to talk, who cares? No, why should see, it's interesting. So, and for that you have to put up with all of this. So it is, and the beauty of this is, that is why, notice that anything you talk about, either a channel, coding and so on, it is not, it cannot cater for all variations of speech sounds. For certain, obviously, because there is that is independent of this. So, and the moment you try to fix one, you get trouble in something else. That is the problem. And because the natural variations are so natural, and you cannot compensate, cater for all possible variations in any design. And that is why, so much of challenge, any design of any system, communication system is still a challenge. Anyway, so this is about all-pole model and so on. Now what we will do with this kind of a background, also this can be written in a slightly different way, which we will use it, what I call it, in fact you can also write this as EP. EP means it is the minimum error for an order P. You can see for a minimum error for an order P. So, whereas E minimum doesn't bring the P explicitly. So, that is why I can write this. And if this EP is divided by R naught, what is R naught? What is R naught? R naught is the energy. R naught is the energy. You can see that here, when m is equal to 0, it is Hz squared. So, R naught, so if you divide it, and you notice that, and you can also see, you can see this is called the normalized, this is the minimum error, this is called the normalized error. Normalized error, and it is given by the following, that is summation AK small r k, k is equal to 0 to P, where my small r k is equal to capital R k divided by. Obviously, R0 will be, small r0 will be, small r0 will be 1. Small r0 will be 1, because you are normalizing it, the first, okay, and all the rest will be like this, and this is, so we have lot to say about this today. We will, but I will erase this, and now I think I will delete all of this. I need a lot of board space. So, get duster. Can I go to the office and get another duster? I don't. This is only dust, not duster. There is no felt here. Just see if we can get it. Okay. Same thing I can do for the so called equations which I have to solve, normal equations, divide both sides by R naught. So, I will get the equations in Rm, small r, clear? So, if you divide it by this, you will get is that clear? So, let us start. Of course, what we have seen so far is the basic formulation and interpretation of the basic formulation, and maybe different types of formulations and so on. And now we will start looking at what is called the solution. Solution of these are called the normal equations. Notice that these normal equations, both are normal equations, whether you use capital R or small r. So, they are called the normal equations, and since these are autocorrelation coefficient, these are called the autocorrelation normal equations. Autocorrelation normal equations. What else could be there? Of course, there could be, notice that last time I mentioned, although I am not going to discuss this in detail, I am not going to discuss that in detail. You can see this correlation. You take a data, and what we are trying to do currently is take this, shift it, multiply, sum, shift it, multiply and sum. You see, and as I told you, if you take a block of data and set it to rest of the samples to 0, when you shift it and multiply and add sum, what are you getting? Each shift, the number of samples playing a role will be reduced. Instead, I can also think of a situation where simply take the data without blocking it first. My data is there, and you identified these n samples here, but you are not doing anything. You still consider all the samples greater than n. Take that whole data and at the bottom shift it by one sample. When you shift it, after shifting, you find this block, that means these n samples. So, you will have n samples in the original and the corresponding shifted value. You get the point? So, now you multiply and add. So, you again shift these by 2 samples, then you can see again you block it. So, you can see in this case still it is a kind of a correlation where as you keep shifting, multiplying and adding, then the value will come down. Of course, some normalization is required, but the value, because the relations will be lesser and lesser as you keep shifting more, at least in a asymptotic way. So, that is called the covariance coefficients. You can also derive the linear prediction analysis. Notice I have carefully avoided putting the limits for Rn. I said summation Sn plus 1, I said n. Depending on what limits you use for n, you can accordingly you will get either autocorrelation or what is called the covariance coefficients. You don't worry about that part of it, I am just saying, because in literature you will find. So, depending on how you use that n for a given block of samples, how that decides whether it is covariance. So, if you use the covariance coefficients, it is called the covariance normal equations. Unfortunately, the term covariance is not correct term as it is explained very well in many books, because covariance is a statistics term or random process term, but it is the term is borrowed in a wrong way and speech people started using, but out of history, we cannot help it, because the original linear prediction analysis was normal equations or covariance normal equations. But anyway, let us not go into the history of this, but the point here is you will get similar equations and the solutions similar, but they will be different, the values will be different and so on. I will, but we are not considering in this course this part of it. So, we will, but I want you to understand the difference between these two, because in books you will find both of these are discussed in great detail. solution of this. So let us carefully consider. I may use interchangeably all of these, so don't you have to understand, and it is doesn't really matter. Here again you can use normalized or unnormalized. These are my normal equations. I want the solution for this. And of course, typically you can always, what is there? These are m is equal to 1 to p. These are p equations and p unknowns. What is the big deal in this? You can always solve them. But the point here is, if you solve them by any standard method, it is you need p cubed operations. You see, typically solving a p equations and p unknowns. But these are not any equations. These are special equations, and that what is special about it? I am not going to write that, but if you really write, maybe I will. If you really write this whole thing, you can write like this: R0, R1, etc., R p minus 1, R minus 1, R0, etc., R p minus 2, and also of course I needn't have written like this, but if you write this, this is what it is, but r minus 1 is same as r1. So you can and likewise r minus 2y, because it is symmetric. You take this, shift it this way or this way, you will end up in the same thing, and that is only for autocorrelation normal equations, but anyway you can okay, this is what you get. So what is interesting here is, although these are p equations and p unknowns, they are not any equations. They are special equations. You can see the speciality comes. What is the problem here? The problem is all r's are known and you have to find a's. And the matrix that is involved in this equation is of this type, which is not any matrix. It is not any p by p matrix, but it is a special type of p by p matrix where you can see all diagonal elements are same, and not only that, any diagonal you take, the elements are same. Any diagonal you take this way from left to right, the elements are same. You will see R1 along this, RP like this. If you go and see any diagonal to this. So, and this such a matrix is called Toeplitz. And I didn't ask for it, it just came as a result of the solution. So because of the special structure of this matrix, but for that of course it wouldn't have been probably that popular in speech at least for another 20 years. Became popular in 70s primarily because even if you knew linear prediction analysis, people would have waited, or it would have been only in the form of papers writing, but nobody would have applied it but for the special structure of this. And what does the special structure do? What the special structure do is, instead of computing this in p squared operations, you will end up in computing p squared operations, p cubed. Instead of p cubed, you will be able to solve these equations in roughly p squared operations. Of course, some exact numbers are not important, and order less. Of course, there is some log and other thing. Don't worry about all of that because of the special structure. And what does it mean in terms of speech? After all, speech, as I told you, it keeps coming every 10-20 milliseconds. You have to deal with the next one. So if you really want to compute this online or something, or real time, you have to worry about finishing all these computations. So reducing it by an order from p cubed to p squared is a big achievement, and that came out as a bonus in this case because of the special structure of this, and that is called the Toeplitz matrix structure, where the diagonal. Because of this, in fact, I am not going to details of this. You see, the solution of these normal equations is a challenging, not challenging, it's a very interesting problem, and which is addressed by over a period of about 60 to 70 years, even before LPC this speech application came. And so solution of normal equations, in fact that was the subject of study for virtually hundreds of thousands of scientists all across the world, in all fields of engineering. And that's why there are books written on it, and of course I cannot go into many details of this. If you see any book on linear least square estimation problems and so on, you will find this. In fact, the starting point will be this, and also it ends with this. That means there is simply they keep discussing this, and there are many interesting. In fact, if you, unfortunately in the electronic library you can't see that, but if you happen to go to library and see some of these IEEE papers in 70s, 60s, 70s, 80s and so on, you will see everything is hovering around this. I am talking about in signal processing. Same thing is true in economic time series, anything, astronomy, anywhere you see, this is a starting point. So don't underestimate the importance of this. Is really very useful to, and so that is why solution. Of course, ideally I would have liked to love to spend time in solving this, explaining all the nice features of this, but again then we will have to skip speech. So let me focus on speech and skip the solution of this. But the point here is, one key idea you can see because of the special structure of this, you instead of, if you want to solve a pth order equation, p equations and p unknowns, you can solve this as two p by 2 equations very easily. You can solve this whole thing in terms of two p by 2 equations. Then why stop there? Each p by 2 you can again solve in two p by 4 equations. Finally, end up in solving 2 by 2 equation. So that means this becomes, in fact, the solution becomes even, that is one way of looking at it. Of course, there are many other. Of course, you may say, what do I do if p is odd? No problem. If p is odd, all that you have to do is, there is a center equation, you repeat it twice. That's all. There is no center step which is repeated. That's not a big problem. And so the whole idea here is, of course, there are solutions also are discussed in great detail in the literature. And so the whole solution, there are several ways of describing the solution. One is what's called the, and another interesting thing here, apart from, so there are many issues here. I don't know, frankly speaking, I don't know where to begin and where to end this discussion on this, but I just highlighting a few things. That is, it can be solved in a lot less computation because of special structure, and one way of looking at it is solving this as a 2 p by 2 and so on and so forth. All that it requires is combining two terms at a time. Instead of solving A1, A2, A3, you solve A1 plus I think AP first together, and likewise A1 minus AP. Like that it goes on, and then you solve them separately and so on. There are many ways of doing it. That is one. But there is another interesting thing that you see here. And the interesting thing here is, when you solve this, of course, by some methods, which is called a Levinson's method, very famous, proposed I think in 50, 60 years ago, is the following, that it is order recursive. What do you mean by order recursive? Order recursive means, if you solve for p order, use the result of that in solving for p plus 1th order. So if you want to solve a p plus 1th order equation, you solve for pth order first, and then you can use that result for p plus 1th order, and so on. So this becomes an order recursive. It is recursive in the order of this. So what does that mean? That means you solve for first p is equal to 1, use that result in solving for p is equal to 2, and use that result in solving p is equal to 3, and so on. Notice, if you say that you are solving that, it doesn't mean that you will get first A1 and in the second time A2 and so on. You will get A1, which is solution for the first order, and A1, A2 will be solution for the second order. That A1 will be different from this A1. And A1, A2, A3 will be solution for third order, where A1, A2 will be different from second order. Please note that. So you need to compute all the coefficients again. But you understand what I am saying? It's very, the reason again I am discussing is, if you decide to forget about speech altogether, you can do that, but don't forget this, because you can just use it in many other areas as well. So that is the advantage. And more importantly, the interpretation, the insight it gives, that's what is important. Okay, that is order recursion, or there are a number of ways of looking at it. And one such solution I have given here, this is called the Levinson-Durbin solution. Levinson-Durbin solution for autocorrelation normal equation, that is what this is, and it is only 5 steps, and out of this also some steps are redundant, but anyway the solution is so simple, but I am not going to discuss the solution here. All I am going to say here is that I want you to look at, of course again it will be nice to derive this, which is very easy, takes only about an hour or two, but the point here is again that much time we lose, but if you solve this, what happens is the following. You see, first of all, what is written here is somehow R naught, I might have messed up a little bit, but strictly speaking it could be capital R. All this should have been a capital R, but small r also it works. Small r it works, then E0 will be 1 automatically. R0 will be 1. So, for some only now I am realizing that I made a mistake by writing small r0, it should be capital R0. Okay. So, but it does not matter. You see, even small r0 also exactly same solution works, no problem at all. You see, then only thing is E0 will be 1, and this E0 is called the energy, and if it is normalized you are making energy 1. You get the point I am saying? So, there is nothing wrong in any of these equations, it is just that how you read. And when you go through this is a, you see, you will get something, it does not matter how you look at it. What is interesting here is, somewhere along the way as you keep solving this, you will get some intermediate values called Ks. I am not going to discuss solution of this. So, what is interesting here is, if you final solution of this is written here, so called LPCs. These LPCs are AJP for j is equal to 1 to p, that means, and that AJP you will get it from here, say from here. Again, don't say if I start explaining that, first my instinct was that I should derive this, it is a very nice derivation, but then I thought I will be wasting at least an hour or two on this, so I will not worry about it. Not because it is that complicated, but it is simply that for explanation I need to spend some time, otherwise it is a very simple solution, and code writing also is just only 5 steps. Yeah. Lot of significance. In fact, now that you raised, I will bring that. I thought I will not bring that, but I will bring that eigenvalues also maybe towards the end of today's lecture or tomorrow. This one. Initially I thought I will not, but now I will. If I forget also, you remind me. So let us go through this. So what my interest is in, so this whole thing will give you a solution basically, and any solution of p coefficients you see, you will get what are called the pk values in this process. So, and the A's, these are the linear predictor coefficients, and when you come out of this loop, you will also have pk values, and those pk values are called this one, Parcour coefficients. Parcour means partial autocorrelation coefficients. Partial autocorrelation coefficients are Parcour coefficients. In fact, or these are also called the reflection coefficients. So that will come out as a, in this particular, there are other types of solutions where it will not come. Please note that if I mentioned several types, some other types of this particular type way of solving this is called the Levinson-Durbin equation. There you will get this case as intermediate step, which will help you to see, have some insight into this. First of all, I said those are, so given case, p case, k is equal to j, j applies for both of these. So given p case, you can get yes or vice versa. But what is interesting here is I want you to see this step here. What I want you to see here is that the, because there is a, this I, you have to collect it after every I is equal to 1 to p. So k you collect for ith one and then store it somewhere, and likewise I is equal to 2, store it somewhere, and so on. So that is what you have to do, and each I, that k that you get is the following. You see, that helps you to find out the total error at the end of That is, let us say if you are at the ith order, let me put it at the ith order. This also corresponds to the ith order. So if you see this carefully, this is the error at I plus I minus 1th iteration. There is a small, what should I say, lacuna in my arguments here, because the reason is I am not describing this fully, otherwise it should, but anyway, I want to, the reason for I need not have written this, I never wrote earlier in many previous classes. The reason I want you to do this is to highlight this point once again. What it basically says is, this is at every I, when you go through, just as you have Ki, you also have Ei to pull out and have a look at it. And that is true for that order also, I. So you can see at the ith order, you will see this is what you get, the energy or the error, not energy, error at the end of ith order solution, let us say. And what it says is, the error at the I minus 1th iteration or order multiplied by 1 minus Ki square. And this Ki is always less than 1. I think I should not less than. Mod Kj can be positive or negative, but it is always less than 1. Cannot be even equal to 1. It has to be less than 1, and because it is less than 1, what happens here? Notice that the error at the next iteration or next order and iteration both work same in this particular interpretation of this. So at the next order, what is happening? The error is coming down. And that is the interpretation I want to bring in. It is also obvious now, coming to think of it, given some data, you are doing a linear prediction on that, and if you increase the order of prediction, what do you expect? The error has to come down. If the error does not come down, what happens? Then the extra piece that you allowed will have to be 0. That means those coefficients have to be 0. That means by adding extra order, if that is not reducing the 0, the coefficients themselves will be 0. That means you are not able to reduce any further by looking at more of the past samples. You looked at past p samples. Now if you want to look at some more samples, the error is not coming down. That means why do you want to look at them? Huh? This is total error. Always remember we are talking about the total error. It is not an individual sample error. Average. Okay. Good. There are a few small catches here. I just want to ignore that because of the truncation, other things, lot of other issues will come. But let us. We are only using our intuition here to say that of course you can all. Why I am a little cautious here is tomorrow you can come up with an example to show me, oh, you can see error has increased, you are wrong. And I can also cook up an example where it is possible because the so-called end effects, the autocorrelation function that you take, all of them may contribute in a few cases, apart from the finite word length effect and so on. But leaving those things aside, you get the point? Finite word length effects are so important here because the numbers that you get are very, very small, most of these, especially that K. Anyway, let me come back to it. So what is interesting here, use the intuition here. The intuition here is linear current value, prediction of the current value based on the past P samples. The idea is if we give more samples, the current prediction should be better on the average. If it is worse, why do you use it? Not for a thing. That is the logic here. So, if there is no further reduction in error, that means the new coefficients that are likely to come are 0. There is no, it's not possible. You get the point? So, that is the idea here. So, that is what I want to, the whole purpose of putting down this equation is done. And in fact, it's only Levinson-Durbin's equation show the detail of K and E. And again, let us look at K a little more carefully. It also helps you to keep monitoring the numerical part of it. After all, when you apply for, put it in a program, you better have some checks, otherwise it can go off. You see, these are all numerical real number calculations, and in a computer you are using a a finite word length, no matter how large the word length is. And there will come a situation where, you see, the numerical errors can propagate in each of these iterations. So you provide a check at every time. What is the check you provide? When you come out of this ki, you keep a check and see that the ki never exceeds 1. In fact, it should not be even equal to 1. If by chance, so somewhere in the loop you put mod k, if mod k is greater than or equal, 0.99 or some limit you set, and if it is more than that, don't even proceed further, set k is equal to 0.99 and then proceed, so that you are ensured that always your equations are stable, solution is stable. So this is a very important, especially you can't say suddenly my speech coding is gone off kind of a thing, you have to worry about all of this. So that's why this check, inbuilt check is provided here in terms of this. That is primarily numerical this one. Otherwise, if the autocorrelation coefficients are exactly these autocorrelation coefficients of a random process or a stochastic process, ideal stochastic process, then question of anything happening, of course this k getting greater than 1 also can be due to R's, because the R's are not exactly true autocorrelation coefficient. They are not ensemble average of the stochastic process. These are all from a finite data and all these things. So there could be a small problem. Fortunately, that problem doesn't arise when you take a long enough data and compute all of this. But it is, in very some strange cases, it can happen. So you can't be 100% sure about this. This is what as a numerical analyst or a computer scientist, we should worry about these things. You see, because you can't say that this algorithm is there, apply, you will get it kind of thing. Okay, so this is this k helps you to check, keep a check on this. And as I told you, k, that means now we should keep that aside. Two things I wanted to bring out there is, one is you will get what is called the k as an intermediate result, and which is called a Parker, and E helps you to again monitor to see that the error comes down as you keep increasing the order. This algorithm is not, you have to be a little more careful here. I have written it correctly, but interpretation, have to be a little careful. My goal here is to show you that I have the solution of this gives me, of course, my P LPCs. I don't have to use LPCs. I can also use reflection coefficient to represent my solution. So I can use, because P and A's are interchangeable, you can solve the P from that, from K's, and vice versa. It's very easy to do, and so you can solve for P's and from A's. And now, why this is a Parkour is, of course, you can show by lattice formulation why it is a partial autocorrelation, but I don't want to go into that. But the point is, reflection coefficient is important for me. I use this reflection coefficient meaning in giving a physical interpretation for this whole thing, at least especially in the context of speech now. Now imagine that as I, this is from a speech production mechanism which has a vocal tract length of certain length, let us say L centimeters, meters, whatever it is. And then what you have is that this vocal tract shape is not uniform. The vocal tract shape is not uniform. So now consider a situation where I have, let us say, in a caustic tube of length L, where this is one is excitation, another is mouth kind of a thing. And now I want to get a decent representation of this through this. Now what is interesting, if you make P is equal to 1, that is, you will get one reflection coefficient, and that one reflection coefficient will enable you to determine this as a 2-tube model. Now it is only 1-tube model of certain thing. That means you can get something like this. Same length, and that reflection coefficient, one reflection coefficient that you get here, when you have a tube, if it is uniform tube, because a lot of you may not know what is wave propagation, but if you still assume some wave propagation, what happens is, when it goes, except at the ends, it will flow freely, there is no problem at all. But on the other hand, even if there is no loss in the tube, if there is sudden change, either increasing or decreasing, you notice that for the propagation of wave there is a change there. So, some part of the wave gets reflected, some part goes back. You get the point? So, some energy comes back and some goes out. Same input energy. So, the portion of the energy that is reflected back is my Ki. So, that is why hence it is called reflection coefficient. And now, if I have P such a, so basically what it means is the same length now, I can't draw all of this, but you can imagine. So, depending on how many sections you want, and in each section you can see that it is, these are all rigid tube approximation. Rigid tube approximation, even if it is a rigid tube, uniform tube, the fact that the areas are changing means that each change there is a reflection. You get the point? So, if we have, and this reflection is simply ratio of this area by this, related to these areas. In fact, you can show K is simply some area, this area by this area or something. You can easily verify that. You see. So, what is interesting here? So, from K's you can in principle derive for the same total length, the approximate areas where the change in the area reflecting the reflection coefficient there. So, given the reflection coefficient, I can approximately construct an approximation to the shape of the vocal tract. You can see where linear prediction, where the approximation to vocal tract. So beautifully it comes, and you understand what I am saying. Of course, I am not going to detail, and so that is what I have. You see, there is a little bit of a, I am not going to detail. So this given K, you can get what is called the areas. Log areas, that means I is equal to 1, this is A1, A2, A3, A4 like this. So, or G1, G2, G3, G4. So, this is the log area, this is anyway, I think I have to be a little more careful here. This is called AI by AJ, that is the area. And from that AI by AJ, you can define a log of that log area coefficient. Why log area coefficients? It so happens again, take your cell phone, this is what is used, or something related to this is what is used for coding, because of the stability of the coefficients and so on. So otherwise, I should have written an intermediate step, what is called the area coefficients. Area coefficients are nothing but this ratio related to case. So you can look into the books for that. So there is no problem. Yes. For? Unfortunately, no. I think we answered that already. Anybody can answer that? For nasal sound, this model itself doesn't apply. Because it's an all-pole model. So, if you try to do that, it will only give the nasal tract shape, but not the coupled vocal tract. Get the point? Each section is uniform, yes. It is an approximation. Huh?
It should have infinite number of cubes.
Of course, yes. That's right. That's why as you keep increasing P, you will get that many reflection coefficients and that much of this. Say it again. How can it be? How can it be reflected? See, this is part of it is going forward, part is coming back. Notice that it doesn't stop there. What comes back again gets reflected back and forth. Please note that this is, I think there are a lot more here. There are at least about a couple of 100 papers on this, and these form almost 1 or 2 chapters in a book on this. So obviously I cannot bring all of that into a small discussion like this, but I want you to give a feel for this whole thing. That is, but notice that this is still a very crude approximation for the simple reason that this is a rigid tube model approximation, whereas my vocal tract is not made of steel, fortunately. You see, So, the soft tissues, how to model, bring them in the model is still a challenge. In fact, even as early as last year, I got a couple of papers for review. Somebody is writing lossless tube approximation to this and so on. I rejected the paper. So, because it doesn't, it's very difficult, very difficult. So, you can see, you can only stretch this only up to some point, not beyond. You should understand this, okay. And in fact, if you, although I want to make it, mention it in the passing, that as I told you, this whole idea of linear prediction, which results in normal equations, solution of normal equations and so on, has nothing to do with speech. If you go out of speech and then go to, let us say, geophysics. Geophysics people exploited 20 years before the speech was exploited using those Ks. And what are those Ks? Those Ks are nothing but the reflection of the different layers of the surface of the earth. You see, if you go down, certain layer in a soils or different layers will be there. Some approximately uniform layer and then another uniform rocky layer and some other layer, waterborne layer like this. So, you assume that there are different layers. So, at each layer there is a reflection. And this is what they have exploited to find out, depending on the values of those reflection coefficients, and with the prior knowledge or approximate knowledge of the model of this, oh, this reflection coefficient is different, so there must be an oil there kind of. That is how it was exploited in oil exploration. And a lot of you people may not know, I think I told you in the class, Texas Instruments is an oil company. It's not a computer company or chips company and so on. Finally, probably they made enough money there or they didn't make, whichever, or they are not making money here. That's a different matter. Okay. But actually, basically, originally it is an oil company. And what they have, I heard their presentation about 30 years ago, how they have beautiful, of course, I didn't, at that time my knowledge also was limited to understand that, but they were simulating the layers of, at various layers and with appropriate thickness, and the natural one they have got, and they were trying to see what simulation would give a similar result here. You see, that is how they tried, of course, different types of soil and so on, what kind of reflections they will provide, and similar. See, after all, ultimately, even if you succeed once out of 1,000 attempts, you are already rich, because once you find the oil, that is enough for you. But it's interesting, you see, because why? You cannot go deep, no matter how deep you find out, you cannot find out the various layers and so on. You can't obviously go deep. So, you have to explore an unexplorable thing, and this is one of the. So, you can see very, of course, this is not alone. This is in economic time series, it has much more nicer stories better stories to look at. And probably in medical, although I have not studied that much, it should be something. You see, you need domain knowledge. Even I don't know much about the geophysics. In fact, I don't know anything about it. You need all that knowledge to even to explain this phenomena. But in fact, if you are curious to know the papers in geophysics journal, there is a journal called Geophysics, and I don't know now, recent last 20 years I have not seen, but in 70s that's what we used to refer very often, because beautiful signal processing ideas used to come from there to be applied to speech and so on. So, that is how so anyway, you can see the story. It's not just, that's the reason why one should not look at it only as a speech signal and something kind of a thing. But of course, our interest is, if you want to look at it as speech, and the more important, what happened is people hammered out these studies, so much they studied to find out, because from communication angle, after all, LPCs, if you start coding, you are in disaster. Because the whole problem is LPCs are nothing but the coefficients of the polynomial, that AZ polynomial, and you notice that every coefficient has to be almost virtually need to be represented with infinite precision. Any finite precision, it ends up in a disaster or close to disaster. So, that is why, how do you overcome that? That is where all these coefficients, log area coefficients came to the rescue. So, they are less sensitive to these coding artifacts. So, get them, and then from there you get reflection coefficients and then LPCs and so on. So, that is how the whole story. So, this is about the solution of these normal equations, reflection coefficients, LPCs first of all, and then the refraction coefficients, and then the area coefficients. Is that all? No, there are many, many more, and I think a few of them I have written here, one more step here. These are what are called the capsule coefficients. You can also express these linear prediction coefficients in terms of capsule coefficients. What do I mean by that? Simply, it is a, because one can make it simpler, one can also make it very complicated. This whole thing has come from a complex variable theory angle. It's much more interesting for mathematicians, but for engineers it's a headache. So the whole thing here is, but logically it's very simple to understand. Log Az you take, and you simply write this as some Bz, doesn't matter what, or Cz. If you write log Z as Cz, what is it that you notice here? You notice Az is a polynomial. So log Z Az also, what you are saying is you express in Cz also is a polynomial. Polynomial means what is 1 plus C1 Z minus 1 plus C2 Z minus 2, like that. And Az is 1 plus A1. So you, even if it is a finite order polynomial there, you can express that here, and you can get C0, C1, C2, C3, etc. How? By equating the corresponding coefficients. You get the point? That's exactly what is done here. If you do that, what happens here is, it's very easy to do, but nice exercise, but again, deviation for me, but it's for some of you should be curious to do that. It takes anywhere between half an hour to a couple of hours, but sometimes you can finish it even in 10 minutes. But this relation between all that you are basically doing is matching the coefficients of this. And when you do that, the beauty of that is you will get these C's in terms of these A's are here in a recursive relation like this. And this recursive relation is, since there are only P coefficients, but unfortunately C coefficients are infinity. In C coefficients are infinity, whereas in A only there are P coefficients. So up to P, this is the equation. And beyond P, use this to get, that's why M greater than P. For M greater than P, you get this. So in fact, if you have this, these are called the LP's capsule coefficients, linear prediction capsule coefficients. Why this became a capsule coefficient? Can anybody see that? It is all there for you to look at. Why do you call this as a C's as a linear prediction capsule coefficients? Why are they capsule coefficients? It is there, solution, answer is there on the board. No? It doesn't trigger? No? No. Why is it C's are called the capsule coefficients? I'll wait for another minute. It is staring at you, the answer. Too much, too many words. Answer is only one word. Too many words. Exactly. I say, if I give any hint, log. You remember we have taken the log earlier? And when you take log and express that as inverse Fourier transform, what is inverse Fourier transform? It's nothing but simply polynomial again. Don't look at a Fourier transform as something very difficult thing. It's nothing but a polynomial only. Fourier transform also is a polynomial. Why? Because e to the power of j omega n. Correct? So I have a polynomial, I take log and then get the coefficients of that polynomial. So that is why it becomes. So what you are basically finding is the coefficients of the inverse DFT of this in some sense. This is. You get the point I am saying? You got that? So hence it is called, and you can see once that hint is there, everything is obvious. Everything is obvious because after all, how does it matter if not Az, if it is minus Az, what happens? It is all the same. Minus Az is nothing but my all pole filter. If my Z is e to the power of j omega, I am evaluating it on the unit circle. So whichever way you want to look at it, you follow what I am saying? So if I just take the specific case of Z is equal to e to the power of j omega and take a minus here, I will get new set of, that is nothing but what is called the this is the spectrum of this you want to call it, and the spectrum, log spectrum of that I am taking the inverse of that. So that is the coefficients of this. See the problem here, see if you have to stretch your imagination, otherwise if I give the solution now you only note down that. You all of you got the idea? It's very, so this is called the capsule coefficients, LPC capsule coefficients. This is called linear prediction capsule coefficients. And the sheer beauty of this is, so given A case, you can get C's. You need only P C's to get A case or P A case to get P C's. Although you can generate up to infinite C's, they are all useless. Useless means you can derive them from the first P C's. So equivalent representation. Given A case, you can get case, or given case, you can get A case, or given case, you can get area coefficients, or given area coefficients, you can get this, given this, you can get C's, given this, you can. So these are a few of the many alternative representations. How many alternative? Again, there are dozens of them. I cannot discuss all of them. So why do you need all of this? So you need some, for example, for coding point of view, I need log area. They examined all these, a lot of people, and said which is the one that is effective when I have to represent it in a finite word length without spoiling the characteristic of that. That is what they have studied. And so from quantization point of view, area coefficients are supposed to vary. Whereas if you want to match two spectra, which is the one that is there? From matching the spectra, the most effective one is the linear filter capsule coefficients. If you want to see whether two spectra are similar, you see, so you go to the capsule coefficients. Okay, you notice that you will have big trouble if you have a spectrum like this, and if I give you another spectrum like this, which is almost close to this as a function of omega. And imagine that this is not on log scale but linear scale. This is log spectrum. So if a linear scale, it will be like this. And now you try to find the Euclidean distance between these two. To find out how close it is, you are in big trouble. Why? Because the distance is very large here. Because this minus this will give large distance, this minus this gives, so total, unless this coincides with this. So any approximate one you cannot have a good distance measure. On the other hand, if you take log, now you are slightly better. On the other hand, you go to the caption and then smooth it, that means truncate it and come back, then you will get both of them something like this. Then there is a good match, because it blunts some sharp peaks and so on. So anyway, some of these we will come to later, but I want you to understand these are the various representations of the LPCs, and you can see just as there are so many formulations, there are so many solutions also, and so many interpretations of the solutions and so on. And it's not all. In fact, as I told you, it's this part alone solution. Now this is about 1 or 2 semesters course. In fact, that is not enough. I used to teach this about long back, about 20 years ago in IIT, when the BTech students were very smart and they were so inquisitive, so that I could fill every day about 5 times the board completely from one end to the other, almost all the 60 hours. I say, so the only solution of these equations, nothing else. And it was why need this? Because you can see the insight a lot more into this. what happens, or you can go right up to the, from signal to the various intermediate stages in the solution, what happens, how to implement it in a you know, hardware kind of a thing, what kind of additions, multiplications that take place, that kind of a thing. Of course, now that was a different course also. I am just saying that we are not even scratching the surface here to understand all of this. But at the same time, I don't want to truncate the thinking and saying, okay, this is what it is and take a case. But at least you should keep in mind that there is simply so much to look at kind of thing. What is linear prediction? Where are the area coefficients? Where are the reflection? Where is the vocal tract shape and so on? It's all very interesting and very, we can see. It goes on and on. It's not that, and ultimately I have to bring in why all of this, because my capsule coefficients are needed for interpretation. Capsule coefficients are needed for my speech recognition, for matching, and so on and so forth. So I think I will stop at this point. I still need at least another class to discuss other representations and also probably some effects of this on the signal. That is, if you perform linear prediction analysis, what happens? How does the signal look like? And what is it that you get from these AKs in terms of speech spectral information and so on? All those things we will discuss tomorrow. Hopefully tomorrow I will try to complete this.